Hi, my name is Ken Crooks. I am a sales engineer here at Phoenix Controls. So there's primarily two concerns from our customers. First and foremost is safety. And by safety I mean the researcher, the chemist, he or she standing in front of a fume hood. That fume hood needs to contain at all times. And safety is job number one, and if that chemist isn't protected at all times, it's loss of human life, potentially. This is life safety equipment. And obviously for a corporation, they want to protect their number one asset, which are their people. The second need of our customers is conserving energy. Laboratories consume a large amount of energy, and so any way we can reduce that energy consumption is an added benefit, but never at the cost of safety for the worker. Fume hoods and their energy consumption have been described as 3 to 5 average U.S. homes energy consumption per year. That's each hood. So you walk into a laboratory and you see 5, 6, 7, 8, 10 fume hoods. Multiply that by somewhere between 3 and 5 U.S. homes worth of energy, you've got a tremendous energy bill on your hands. So obviously anything you can do to reduce that is a good thing. So Phoenix Controls, with our Venturi valves that meter flow, not measure flow, are unique in the industry. No one else does it the way we do. We do not measure directly airflow itself. There are a lot of concerns with doing that, and especially in the most critical environments, which is the toughest thing, is to say in your most critical environments, don't do what you're accustomed to. Don't measure flow, meter flow. But in fact, metering flow is a safer approach for laboratories. It's the most reliable, the most accurate, and the fastest responding system in the industry. We are industry leaders because of that. At the heart of the Phoenix Control system is the mechanically pressure-independent Venturi valve. That's what sets us apart from everybody else. The fume hood containment demonstration that we do here at Phoenix Controls and all of our customer visits is very dynamic. We have a smoke machine inside a fume hood so you can visualize the airflow patterns. And we operate that in a Phoenix mode, which is that less than 1 second speed of response. Move the sash into various different positions, openings, closings, and we see that visually from that smoke, proper containment at all times in all positions. We'll then slow it down and we'll simulate what a flow measurement system would respond like, both at 3 seconds and also at 6 seconds. And you can see that at either of those settings, there is a loss of containment of that fume hood. It will not contain properly. And unfortunately, most of that loss is right into the breathing zone of the researcher, and that's what you don't want to happen. After the primary containment zone, the fume hood itself, is demonstrated, we'll then take it a larger step. We'll look at the laboratory itself. The lab proper, if you will, is the secondary containment zone. And so that laboratory must maintain negative pressurization in relation to the corridor or its adjacent spaces at all times. And how we do that with the Phoenix system, we sum up all the fume hood requirements of that space, the total exhaust signal. The makeup air, the supply air in that space shall always be something less than that. And that volumetric offset is a fixed volumetric offset. So as the sash position moves, the supply moves with it. As we close that sash, the supply will move down with it. Again, maintaining that volumetric difference and therefore the pressurization relationship with the laboratory. If there's ever a spill in that laboratory, the lab will contain it. So first off, we're variable volume. And by variable air volume, I mean you close that sash, we reduce the airflow. If the open area is smaller, the airflow required to maintain that constant velocity through that opening becomes smaller itself. Otherwise, the velocity would change. So by reducing the airflow, we're reducing the energy consumption and maintaining safety. Additionally, if a user has a fume hood that they're no longer going to use for a period of time, the researchers are going off in field study, if the fume hood's not needed for ventilation, if it's not needed for containment of stored chemicals and whatnot, they can close that sash and drive the valve down to minimum position. And that minimum position with a Phoenix shutoff valve can be 0 CFM. Additionally, along that same thought is the general exhaust valve. We can drive that to a shutoff mode when the fume hoods are in use and there's enough exhaust air already going out. Why introduce additional exhaust air, the minimum flow of the general exhaust? So we'll drive that down to 0 CFM during normal use. And this is all automatic, part of our control system. Phoenix Controls customers, whether they be the engineer designing the building, whether they be the occupant standing in front of the fume hood, or the owner of that building paying the energy bill, all enjoy by design a system that will reduce their energy consumption, maintain safety at all times, and be reliable day after day, year after year. No flow sensors to drift, no clogging, nothing going on there that's going to undermine the reliability of that system. That engineer has confidence in his or her design, their stamp, it's approved, it's going to work day to day. Energy consumption is going to be minimized and user safety is going to be maximized. Safety, savings, satisfaction.